Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 3 of Arrow 4080. Today we're going to be extending our study into finite elements by including truss elements and also looking at transformations of those truss elements in a two-dimensional system. Let's take a look at how that works. All right, starting off with our nomenclature, let's just take a look at a truss element. Once again, as we saw with springs, we're going to have an element. Before with springs, we just had a spring constant K. But when we have a truss element, we're basically going to have an area and a length. We're also going to have two endpoints. A truss element can take axial load, and that's all. Now you can also use a truss element that takes torsion, but we're not going to address those yet. Okay, so we have two ends, the first end 1 and end 2 at joints 1 and 2. We can talk about the displacements at those ends in local coordinates and the forces in those. Okay, so we see we have a constant cross-sectional area. We're assuming that. You can use the same approach for something that has a non-constant cross-sectional area by just using the average area. If you want to have a cross-sectional area that changes, we're going to need a more complicated formulation than what we're going to address today. So we have constant area, constant modulus, and a certain length. We're assuming it can't take any shear or bending moment, and we're also not allowing this particular element to take any torsion either. We'll look at torsional loads later. Okay? So we can write our equation. Once again, we're using T to talk about the tension in the rod. The force in the rod is just going to be AE over L. The force, if we take the second node displacement minus the first node's displacement, then that gives us a tension force. If we took 1 minus 2, that would give us a compression force. Okay, so from our force equilibrium relations, we see we can write the equation this way. This is just going back to the deflection is just PL over AE, and it's a reformulation of that. But now our displacement is just the difference in deflection of those two ends. Okay? And once again, at node 1, we're calling this a negative because remember this equation, the way we wrote it is for tension, and we're talking about the positive x local coordinate system is going from node 1 to node 2. Therefore, a positive value of U2 minus U1 will give us a tension, which would be in the negative positive direction. Okay? All right, so we can write our relation in matrix form as we did with springs. Our forces at the two endpoints and local coordinates are just the spring constant K times the displacements. Once again, now this is identical to what we saw for springs. The only difference is instead of just being a K in each entry here in the table, our K is actually AE over L. So we can think of a truss element as simply being a spring with a spring constant of AE over L. We can then write that in this format here like we did before, where our spring constant is simply, or our stiffness is simply AE over L times a little 2 by 2 matrix, 1 minus 1 minus 1, 1. Sound good? So, okay, so our sign convention, once again, we have two nodes. We have defined positive as node 1 to node 2. That's what defined all of our relations. This is our basic force relation in local coordinates. And we can, these are our local forces, these are our local displacements, and this is our stiffness matrix. So this is a summary of the 1D truss element in local coordinates. Okay? Identical to springs except for the different spring constant. All right. So if we just look at an example real quick, let's just say we have 3 truss elements. Let's say we have fixed at the two ends or pinned at the two ends. These are our dimensions. You can see the lengths already in the diagram. And let's say we want to find our global stiffness matrix, our displacement, our reactions. This means we're going to need to calculate our local stiffness matrices. We're going to have to assemble those into a global stiffness matrix. We're then going to have to impose our constraints and then solve the equation. If we do that, I wrote a little MATLAB program that does that. First, it echoes our nodes where all of those are located, 1, 2, 3, 4, x, y, and z coordinates. We have our echo of property shown here, and this, then we can write our element stiffness matrices, which are shown like this, where we plugged in the AE over L into the matrix. We can then assemble our stiffness matrix looking at the nodes. At node 1, we only have an entry from element 1. At node 2, we have elements 1 and 2. And at node 3, we have elements 2 and 3. And node 4, we only have element 3. That's our global stiffness matrix. If we impose our boundary constraints, we see that those 2 rows and columns go away. We solve our 2 by 2 and we get the 2 displacements that we don't know. Once we have those, we can plug those displacements in along with our known forces. We know we have a 3,000 pound, we can just multiply our global stiffness matrix times these 4 displacements. That will give us 4 external forces. The external force at node 1 is just the reaction at 1. The external force at node 4 is just the reaction at 4. The external force at node 2 better be 3,000 pounds in the positive x direction, and at node 3 it ought to be 0. And if we solve this, we find that that's actually true. That's all there is to it. Okay? Now, once again, this has got all of the rods aligning along the same, where our local coordinate system is identical to our global coordinate system in the same way we saw in lecture 1. However, that's rarely going to be the case for any kind of meaningful structure that we might try and use finite elements for. So we need to learn how to analyze these in 2 dimensions. Now, eventually we're going to get to analyzing these in 3 dimensions for simple elements. But before we do that, we need to extend our transformation into 2 dimensions so we can look at the differences then. That's going to make it a bit more complicated, still very doable. Okay? Stick with me. So this is what we're covering now, 2-dimensional trusses. All right. First, we need to look at our transformation equation. So let's just say we have a single truss element. We have node 1 and node 2 located out in 2 space somewhere, okay? So that means we have an x and a y coordinate for each node. Now, to keep this simple, let's just look at our rod, which is at some orientation. And remember, the local coordinate system for that rod is going to be along the rod. So if this is element 1, or excuse me, node 1, and this is node 2, then our local coordinate system is going to be going from node 1 to node 2 in this direction. This is where we can write our equations. Now what we're going to focus on at this moment is looking at saying, okay, what are the global coordinates of this node? Well, in local coordinates, this node was at 0 and this node was at the length of the bar. In global coordinates, we're going to have an x and a y coordinate for both. Okay? All right. So if we write that, we see that the x and the y coordinate is simply a trig function. Okay? So if we say the local coordinate system, if we define our local coordinate system as being, or the local coordinate u1, that position 1 is just our u1 with no prime is going to be our global coordinate, and with a prime is going to be our local. Therefore, if we take the position of node 1, the global u and v coordinates, so we're saying u is like an x direction and v is like a y direction, okay? So in our global coordinate system, we have dimensions u and v, and each of those times the sine or the cosine will give us the location. So if we know that our node 1 is at some value u1, v1, then we multiply u1 times cosine theta and v1 times sine theta, and we get what the position is in local coordinates of our rod. And if we do the same thing for node 2, we get this second equation, okay? If you have any trouble with this, you can go back to section 3.3 of your textbook, and Appendix A will help with that, okay? So with that said, we now have a transformation for these. Our truss is located at some angle. Our local deflections are U prime and V prime. Our global deflections are U and V. C, we're going to call C our cosine of the angle of that rod, and S is the sine of that. So we can now transform this by saying, all right, if we use our global coordinates U and V, plug in those values, multiply it by cosine theta minus sine theta, cosine theta, that matrix, that will give us our positions U and V in local coordinates. Got that? Okay. Now, this means our displacements were just U and V. Before they were just U, because we're talking one-dimensional analysis. Now we've got two-dimensional analysis, so we've got both U and V, and or an X and a Y kind of component. Okay? We're going to call this the global. We're going to give that D for displacement a G subscript for global. Okay? We're going to use a capital L for local, or we will just use a prime for local, as you see here. And if we put a little subscript G, that means we're talking global coordinates. Okay? So we can call our local D prime, that's what your textbook uses, or D local, which is what I like to use. The textbook uses D for the displacements, and we're going to use D sub G for global. Okay? Therefore, a transformation, we're going to define a transformation matrix. We're going to call it T1 star. Okay? The reason I'm calling it T1 is because this is we're transforming, this is our transformation matrix of the one-dimensional element, and this is the T star version. We're also going to have a T version. So the matrix is just CSS minus SC, where that C is just the cosine of theta and S is just the sine of theta, okay? So more generally, then we can write that our local displacements are simply our global displacements pre-multiplied by this matrix T star that we just defined here. All right? These little building blocks. Stick with me. If we look at a little example now, just to drill this home, we can take a two-dimensional a truss in two space, just a single element. We've got an angle like this. We've got these two displacements, U2 and V2. These are our global displacements. If we want the local displacements for that node, then we would just apply the transformation, and it gives us our answer. Okay, you can try this out on your own. All right. All right, so we have a one-dimensional truss element, but this is located into space. With the one-dimensional element, we only had a single displacement for each of the nodes. So we had two displacements, one for end 1 and one for end 2. When we go to a two-dimensional system, our global displacements will have two coordinates, a U and a V for each node. Okay? So this was our sign convention. This is our force deflection relation. This is in local coordinates because it's got the prime here. And we can apply this relation. And our local stiffness matrix, then, we can call that K prime is what the book uses for that local matrix. This is how it's defined, and we're going to call it the stiffness matrix, the element stiffness matrix. We're going to use a capital L for local, and we're going to call this L2 because this is a 2x2 version of this. We're going to find that we need a 2x2 and a 4x4 version. 2x2 if we're just dealing with a singular element, but a 4x4 when we're dealing with a two-dimensional system. Well, later we'll find we need an even larger one dimension to deal with 3 dimensions. Okay, so if we want to perform two-dimensional operations with two nodes, each of which have two displacements, one in the X and one in the Y, or one in the U and one in the V, we're going to need to expand this. What this means is this 2x2 matrix will expand into a 4x4 like this. We're still talking this is a local matrix, and we can use a little subscript S to show that it's then a square matrix, or we put it together, or we could use a 4 for this, 4x4. Okay, so we're going to call, now you'll notice up here, we call the local stiffness matrix of the element itself K sub E capital L 2 to show that was a 2x2 matrix. When we're using the 4x4 matrix for 2 space, we're going to call it K sub E L. with no other subscript, because that's the one we're going to need for two-dimensional analysis, okay? So this means we can write our original relation instead of just our local coordinates f1 x prime, f2 x prime, and this guy, we'd have f1 x prime, f1 y prime, f2 x prime, f2 y prime. And that's going to be our local coordinate, our local stiffness matrix times our local displacements. Okay. Now once again, in that local coordinate system, we're not going to be getting forces in the local y at either node, displacements or forces, because it has no stiffness there. But this is setting up so that when we go and transfer, that we can put together our global stiffness matrix after we've transformed this. And we're going to need to do this as an intermediate step. Okay. So we can write it this way. Either of these two ways are equivalent. These are identical and will provide the same results. However, in order to do our analysis, sometimes we'll need to use one and sometimes the other, and sometimes we can use either one. All right. Now, our deflections and our forces in the 1D element are related to our two-dimensional components. This is our transformation equation. We called this transformation T star, and we can now use that transformation, a 2 by 2, we can expand it and transform our deflections from one where we've got u and v in the global transformed into the u and v in the local by just applying this transformation here. Okay? We can call this T star 2. Now we called the other one T star 1 because that just translated our one-dimensional element. This is going to take our two-dimensional global deflections and turn them into the one-dimensional local ones. And so we're going to call this T star 2. Okay? We said this, I think. And now we can say, all right, our element stiffness matrix. So we saw before, we started with our element stiffness matrix in the local. We expanded that into the 4x4. We then transformed it. And we can actually do that all in one step by taking our KEL2, our little 2x2 version, and we're going to pre-multiply by the inverse of the T star and post-multiply by T star. And that will give us the global elemental stiffness matrix, or the element stiffness matrix in global coordinates. Once we have that, we're ready to assemble our global stiffness matrix. Okay? That means our stiffness matrix for the element is going to look like this. Okay? We can use this as we assemble our global stiffness matrix. We're then going to take this, and once again, we will define this with what each node are. Now remember, or what each node is. Remember before we said node 1, node 2, but now what we're going to do is say node 1 in the U, node 1 in the V, node 2 in the U, node 2 in the V, node 1 in the U, node 1 in the V, node 2 in the 1, node 2 in the V, in the U and V. Got that? So that's how that relates with this 4x4 matrix. Having done all that, we're going to construct our global in the same way. We'll make a large matrix with each node 1, 2, 3, 4, whatever they are, but each one is going to have U and V coordinates. And in the same way, this way also, and so on. You see how that works? Okay. So now, once we have constructed our global stiffness matrix, we can use our external loads to solve for the displacements. We're going to have to then, once we construct the system, we'll impose our boundary conditions and solve as we did before. Okay? So, just to kind of summarize here, this is what we have. We have our truss transformation matrix, T star. That's for the two-dimensional system, right? We saw how this can transform our element stiffnesses. And this gave us the T star square matrix, we're calling it, right? And we can transform from global coordinates to local coordinates using the T star, just like this, either of those. Our displacements and our forces. This is what we did to convert our element stiffness matrix into global coordinates. We can also use this secondary transformation. We're going to use T2 star S with our KEL. KEL was that full matrix, and the KEL2 was a little 2x2 matrix. Okay? That's how we can do this. All right. So let's think about this a minute. We know how to construct a local stiffness matrix for the spring, and now we know how to do the same thing for the truss. We now see how we can also transform our local matrix into a global stiffness matrix, still of the element by element. We can use the same approach for our springs that we saw for the trusses here. And we're going to solve our system the same way. Okay? All right. So let's look at an example. Example 3.3. Here we have a little truss in space. We have a length and an angle. We have an area and a modulus. What we're looking for is the global stiffness matrix. So we're going to start with a local stiffness matrix. We're going to transform that. So here are our nodes. These are the properties we have for our nodes. These are the little direction cosines for those nodes. And using that information, we can write our 2x2 local stiffness matrix and transform that into a 4x4 local stiffness matrix. We then apply the transformation in order to get the global stiffness matrix. Since this is the only element, then the elemental global stiffness matrix is the same as the whole structure's stiffness matrix. So once again here we have a one-dimensional truss, and let's think about how do we now compute stresses. Well, stresses are simply P over A. So once again, if we remember, once we get in local coordinates, so stresses will typically be in a local kind of coordinate system, right? So if we have our displacements and we calculate our forces, we could just take our forces and divide by the area of the rod. That will give us what our stresses are at each end of the rod. That's one way. Okay? Another way, this is a good warning here. We got to be careful about these stresses. Remember, just like our forces were not tension compression. Our forces were positive if they were aimed in the element local positive coordinate system, and negative if they were in the opposite direction. So when we use those, we're going to have to take care to figure out what is our local coordinate system for that element, and make sure that we then convert that into either a tension or a compression if we actually use the number. Okay? Another method for calculating our stresses is simply to use the displacements with Hooke's law. Remember, our stress is simply E times the strain, right? EE. And we can use that since the strain is simply the displacement divided by the original length. We can then take the modulus divided by the original length of the element and multiply by this transformation matrix, and that gives us this little matrix here. We can just take our global deflections and multiply by this C sub P of the element. Okay? Here's a little example. Let's say we have a truss oriented in two space. Here's the length and the angle and the areas and the modulus. And if these are our displacements, let's say we want the stresses. The easiest way to do that, since we already have the displacements, the global displacements, take those global displacements and multiply it by our CP of the element, which is shown there, and that gives us our stresses. The other way is to go through the whole process, calculate the forces, and that can do the same thing. Here's a summary of our method. We're going to model our system with nodes and elements. We're going to determine the spring constant for each, or the stiffness matrix for each and every element. We're going to transform our stiffness matrix from a local to a global coordinate system. We're going to assemble our global coordinate, our global stiffness matrix as we did before. We're going to apply our boundary constraints, whether they're homogeneous or inhomogeneous. We're going to impose our external forces. We're going to solve the reduced system of equations. Once we've done that, we then can use those displacements with the other displacements that we knew in order to calculate what our global forces are that are unknown. Once we have those, we can use those global forces and global displacements to calculate the global forces in each and every element in global coordinates. Once we have those, we're going to need to transfer those into local coordinates so we can do anything with them. A force in like some arbitrary x direction is meaningless to us. What we need to do is translate it into a tension or compression along the element, and that's that local force. Okay, and then if we need to, we can calculate our stresses, which we already covered. That's all we got. You're going to want to make sure that you take the time with the homework, not just to get it done, but to understand it. So these last two lectures, these are the first two lectures of the class, and you already have a firm foundation for how the finite element method works. You actually have a lot of work to do in these two lectures in order to really understand what we're doing. If you take the time now, you're going to find out this pays dividends, because we're going to get more and more complicated. We're going to start dealing with more and more elements, a little more terms in our matrices. The same basic approach is going to be applied. And then as we start focusing on some of the programming with Nastran and FEMAP, we'll keep reinforcing these basic ideas for hand calculation so that you get stronger and stronger by the time we finish this class. Enjoy.